public square sits on the 22nd floor, yet functions as ordinary street level. Trains pass through buildings nearby, but the real cause lies beneath the spectacle. Chongqing did not flatten its mountains. It built roads, towers, rail lines, and public space around them. In a municipality of roughly 35 million people, a doorway can open onto one elevation while traffic moves far below another. I used to think the city's 8-dimensional label described visual confusion. It is really evidence of relentless engineering under pressure from cliffs and rivers. In this video, we examine how Chongqing turned hostile terrain into working urban ground, and how that same building drive reaches across modern China. One short video turned a mountain megacity into a global puzzle. On my own channel, the earlier Chongqing footage drew roughly 30 to 35 million views. Once unauthorized reposts across several countries were included, its total reach was estimated at 600 to 700 million. About 3 years later, that reach gives this return unusual pressure. The clips were memorable, but they explained almost nothing. Trains enter buildings. Roads cross above rooftops. A doorway can meet one road while the opposite side opens dozens of floors above another. The internet calls this an 8D city. It is not a planning term. It is shorthand for a place where street level refuses to stay fixed. Chongqing covers about 82,000 square kilometers, joining a dense core to satellite cities, towns, and rural counties. Mountains squeeze the buildable ground. The Yangtze and Jilin cut through it, forcing roads, rail, towers, and footpaths to stack instead of spread. The real subject is not internet spectacle, but the work required to keep millions moving across broken terrain. What stands out is how Chongqing turned its hardest limits into daily infrastructure. The global reaction makes this return exciting. The engineering makes it necessary. Public square sits on the 22nd floor, yet it works as ordinary ground. At Kuixinglou, buses and cars approach at pavement level, restaurants face the street, and pedestrians enter without climbing a visible tower. The shock waits at the edge. The same plaza aligns with the upper floors of buildings that rise from a much lower road. This is not a rooftop ornament. Bridges, lifts, and internal corridors make the square a working junction in the pedestrian network. The terrain leaves engineers little choice. Steep ridges are split by the Yangtze, the Jilin, and smaller valleys, while scarce flat ground must carry intense urban growth. Flat City can assign one street level to one address. Chongqing cannot. One building may have several entrances, each meeting the ground from a different side. Height stops being empty distance and becomes usable frontage. That changes ordinary work. Shops gain customers high above the lower road, and residents weigh stairs, elevators, bridges, buses, and rail for every crossing. The 8D label sounds like an illusion, but this is daily logistics under pressure. At Kuixinglou, altitude itself has become usable ground. An old riverside district now faces a skyline, carrying a 300-meter structure across 4 towers. Below, the Yangtze runs about 6,300 kilometers from the Tibetan Plateau to the East China Sea. The old district climbs stepped ground above the river because Chongqing formed where water transport, mountain routes, and defensible high ground met. Lanes, terraces, retaining walls, and stone steps preserve the routes used before modern highways when people and goods had to follow the slope. Shops and food stalls now handle heavy visitor flows. Hanfu, tiled roofs, wooden facades, and gates create settings for photographs while feeding a tourism economy. It is not an untouched ancient town. Older fabric stands beside restored and adapted buildings, making preservation part of a working economy. Across the water, Raffles City Chongqing answers the terrain at another scale. Its 8 towers place extreme vertical construction beside an old river corridor. The crystal spans 4 towers, roughly 300 meters from end to end. The structure turns scarce ground into occupied height. Old lanes and modern towers share one river frame. The same hard slope now carries routes inherited from the past and a 300-meter structure built for the present. One of China's hardest urban landscapes carries a name that means celebration repeated. Nearly 900 years ago, Zhaodun rose twice in quick succession, first within the imperial line, then to the throne. That year, the occasion became a double celebration, and Gongju received a new name, Chongqing Fu. The character still means celebration repeated, preserving that political event in the city's official name. Before that renaming, the region had been tied to ancient Bei'e and had also carried names including Yuzhou and Gongzhou. Dynasties changed the label, but mountains and rivers kept imposing the same limits. Mountains narrowed usable ground. Major rivers gave trade, defense, and administration a reason to hold this difficult position. Its narrow routes, courtyards, tiled roofs, and buildings fitted to uneven ground are not decorative leftovers. They show how settlement bent around the slope because the slope would not yield. Used to think the name was simply an appealing translation, but the modern city still occupies the same ground that forced earlier builders to adapt. The city's scale becomes more memorable because double celebration marks a metropolis built level by level against mountain and river. Every few minutes, a train vanishes into a 19-story tower while residents above are shielded from its force and noise. At Liziba, Line 2 occupies the 6th through 8th floors, with shops below, homes above, and trains arriving only minutes apart. The spectacle looks impossible, but it began as a land problem. Diverting the route around every occupied slope or clearing the site would carry its own cost. Planners chose integration instead. The station and tower share one envelope, while their main structures remain separated. Rubber-tired straddle-beam trains handle tight curves and steep grades suited to Chongqing's terrain. Vibration-isolating materials and enclosed track sections then cut the force and sound reaching residences. That protection matters because this is not an occasional demonstration. During busy periods, service can return every few minutes, pressing engineering into the daily rhythm of the building. Below, visitors time open-mouth photographs as each train appears to disappear into the concrete. A working compromise among residents, rail alignment, station access, and scarce land has created its own tourism economy. The visual trick is not what I admire most. The restraint is. Liziba threads frequent rail service through occupied floors while keeping structure, vibration, and noise under control. A nighttime landmark can begin at street level and end roughly 12 floors lower beside the river. At Hongya Cave, the cliff compresses restaurants, shops, food stalls, and huge crowds into a narrow stack above the Jialing. The complex is a modern reconstruction, but its stacked roofs recall Chongqing's traditional stilted hillside buildings. That older form solved the same basic problem: how to occupy a slope with almost no flat ground. Here, architecture does more than frame the skyline. It funnels people toward elevators, staircases, road crossings, and a small number of clear viewpoints. Warm light on the roofs, the illuminated Shibaozhai Bridge, and towers across the river pull attention toward the same edge. At peak periods, the crowd can extend for hundreds of meters. The appeal depends on density, and density slows everything. Views close, foot traffic tightens, and nearby streets absorb the overflow. Vendors keep stalls moving while transit staff and police hold barriers, crossings, and pedestrian lanes together. The spectacle works only because ordinary shifts manage extraordinary pressure. The skyline is formidable. The dense crowd beneath it reveals the city's pull. Hongya Cave overwhelms because mountain, commerce, transport, and pedestrian pressure meet on one narrow slope. A bridge here must cross more than a river. It must reconcile a city arriving at the water on different levels. Opened in 2009, Kuixinglou Bridge carries its steel arch over a main span of about 550 meters and stacks several transport modes on 2 decks. The upper level carries road traffic and pedestrians. Below it, urban rail and more transport space occupy the same narrow crossing. That stacking is not a flourish. Steep banks, dense neighborhoods, and approach roads at different heights leave little room for separate links. The bridge solves the shortage by building upward, extending Chongqing's vertical planning from towers into the transport network itself. Its long central span also keeps major supports out of the Yangtze navigation channel, where working vessels still need a clear line through the city. One structure must carry commuters, freight, rail service, and road traffic while resisting wind and changing river conditions. The approaches then climb back into the hills, feeding districts divided not only by water, but by sharp relief. Its scale comes from compression, not excess. Road, rail, river traffic, and steep ground are reconciled in one disciplined piece of steel. road junction built on flat ground, can spread outward. Huangjuewan had to rise through the mountain. The result is a 5-level interchange with around 20 ramps, distributing vehicles among several major routes in southeastern Chongqing. From above, the roads seem tangled. At ground level, every curve answers 4 hard limits: destination, gradient, clearance, and stable ground for the piers. Broad cloverleaf would consume land the slopes do not provide. So ramps pass above and below one another, then meet surrounding roads at different elevations. This saves horizontal space, but transfers the pressure to drivers. Lanes must be chosen early, because barriers and height can turn one missed exit into a substantial detour. Below the decks, engineers must inspect a second maze: drainage, expansion joints, retaining structures, lighting, and columns packed into difficult ground. None of that hidden work stops simply because traffic continues overhead. What looks excessive is actually compressed necessity. Traffic volume demands capacity. The terrain denies width, engineering responds with height. From the driver's seat, the 5-level spectacle becomes a practical rule. Choose early, or the mountain turns one missed ramp into a long detour. Long before the reservoir rose, builders turned a sheer cliff into a 12-level road to the temple above. At Shibaozhai, 9 lower levels took shape during the Qing period, while 3 upper levels were added in the 20th century. This is not a tower placed beside the rock. Its timber frame follows the slope and turns the cliff face into an internal route. Stair flights, windows, and projecting eaves carry movement upward within the building. Before that internal route existed, reaching the temple required a much more difficult ascent. That first achievement belonged to builders working with timber against severe relief. The pavilion did not remove the obstacle, it made the obstacle usable. Much later, the river changed. The Three Gorges Reservoir raised the surrounding water level, putting the base at risk of submersion and forcing modern engineers to defend the site. They built a protective embankment around it. The old riverbank hill became an island-like enclosure, now linked to land by a bridge. What stands out is its double adaptation. Old builders turned a cliff into a vertical path. Modern engineers held back an altered river, keeping the red timber locked to the rock at the Yangtze's edge. An ancient ritual vessel has been stretched into Beijing's tallest building. China Zun rises about 530 meters and stacks more than 100 floors above the capital's central business district. The name comes from the Zun, a narrow-waisted vessel with a flared mouth. The tower does not merely copy that outline, it forces it into the loads of a supertall. The base tightens through the middle, then opens near the crown. That upper flare creates valuable floor space, but it also catches more wind and places greater demands on the frame. Beijing adds another pressure. Strong winds and seismic risk mean height must be controlled, not simply achieved. A reinforced concrete core, perimeter framing, outriggers, and massive foundations share the strain. Together, they limit movement and keep high-speed vertical circulation working across more than 100 floors. What stands out is the refusal to separate identity from engineering. The ancient profile creates the shape, and the hardest structural demands follow directly from it. Height limits elsewhere make this tower a deliberate marker for Beijing's newer business district. To me, its achievement is concrete. A ceremonial form became a 500-meter test of wind, seismic risk, and engineering ambition. The steel that looks most chaotic is doing the most disciplined work. Built for the 2008 Olympic Games, the bird's nest wraps a separate concrete seating bowl in an immense interlocking steel shell. The pattern is irregular by design, but not ornamental clutter. Its members support the roof while hiding stairs, service routes, and circulation inside the dense frame. That separation is crucial. The concrete bowl and steel exterior answer different loads, so each can move and work on its own terms. Every section demanded precise fabrication and welding. Engineers also had to protect the steel from fire and monitor how the vast frame changed under load. Translucent membrane areas admit daylight and block weather without turning the roof into a heavy lid. Even shelter had to preserve the lattice as the building's public face. The stadium returned for the opening and closing ceremonies of the 2022 Winter Olympics. That made it the central stadium linked to both summer and winter games. Its hardest long-term test is ordinary use between global events. The engineering victory remains incomplete unless structure, access, and national image can support a life beyond ceremony. One of Beijing's largest cultural buildings hides its front door beneath a lake. Opened in 2007 beside Tiananmen Square and the Great Hall of the People, the titanium and glass ellipsoid holds three principal venues beneath one shell. Its artificial lake is not a decorative margin. The water mirrors the full curve and separates the building from roads and monumental government architecture nearby. A conventional door would break that surface, so the main approach passes under the lake. The submerged passage turns entry into a controlled shift from surrounding streets into the performance complex. Inside, large shared foyers divide crowds among an opera house, a concert hall, and a theater. That clear circulation is essential when three major venues work beneath one roof. The calm exterior conceals the real pressure. Acoustically isolated halls, stage machinery, ventilation, emergency routes, and audience movement all compete for room inside the same curved envelope. What stands out is the discipline required to keep such a complex machine visually quiet. The shell reveals almost none of the labor needed to make three venues function. That is what astonishes me. Beijing made a massive civic building feel light by forcing every heavy requirement beneath one clean ellipsoid. glowing sphere turns human movement into part of a library's collection. Designed by MVRDV with the Tianjin Urban Planning and Design Institute, the building wraps that central auditorium in white terraces that serve as stairs, seats, routes, and shelf-like surfaces. From outside, the opening and facade form an iris around the sphere. That is why the auditorium is known as the Eye. The geometry does more than stage an image. It lets visitors occupy the architecture, climbing, pausing, reading, and gathering across one continuous interior. Yet the apparent shelves tell only part of the story. Some high sections use printed images or decorative panels, while working collections and conventional reading rooms sit beside the atrium. That distinction matters behind the spectacle. Staff routes, storage, study space, and safety controls must keep a public library functioning every day. The main hall can shift from circulation space to lecture room and meeting place. Architecture becomes civic machinery. It attracts people through wonder, then gives that crowd a place to learn and gather. The way I see it, the future here is not the glowing sphere alone. It is a library that turns circulation, public life, and knowledge into one working interior. A concert hall on a northern wetland appears to have no fixed front, back, roof, or wall. Completed in the mid-2010s, Harbin Opera House occupies Harbin Cultural Island near the Songhua River, where severe cold, ice, and large temperature swings punish every exposed surface. Spale aluminum and glass erase the usual break between wall and roof. Mad architects drew these curves from snowdrifts and surfaces pressed by persistent northern wind. This is not climate used as decoration. The shell organizes approach, shelter, ascent, and entry across open ground where winter conditions can dominate movement. Public path climbs over the building, reopening views across the river. The structure does not seal itself from the wetland. It controls when exposure returns. Inside, warm timber lines the main auditorium and a smaller performance space. The material shift creates visual warmth, while the halls must hold sound with precision inside an irregular outer shell. Curved lobbies guide audiences through that shell and frame-changing contact with the surroundings. Every sweep has work to do: move a crowd, block the cold, or prepare the ear for performance. That is the imagination I admire here. Every curve is forced to work. One of the world's tallest buildings meets the wind by twisting into it. At more than 630 meters, with over 120 above-ground floors, Shanghai Tower rises over Lujiazui as the tallest of three supertalls. Its outer glass skin rotates around a more regular inner structure. Wind testing shaped that rotation, reducing pressure on the facade and frame compared with a simple rectangular form. The twist is not decoration. It is a structural answer to a force that grows harder to control with every added floor. Between the two skins, tall atriums divide the tower into 9 stacked zones, Shared spaces and gardens are intended to make each zone work as a vertical neighborhood rather than an isolated stack of offices. Yet height is not achieved by structure alone. High-speed elevators, refuge areas, mechanical floors, a tuned mass damper, and a deep foundation make daily occupation possible. Beside the Jinmao Tower and Shanghai World Financial Center, it completes 3 generations of super-tall design. Yet this height still demands immense energy, maintenance, and daily coordination. From the skyline, the twist reads as ambition. Inside the frame, it is wind control repeated floor by floor. Suzhou's boldest gateway is a building people can live and work inside. Rising about 300 meters beside Jinji Lake, 2 occupied towers lock together near the top to form one inhabited arch. That connection is more than a visual stunt. Heavy transfer structures carry gravity loads between the legs, while the towers must still move safely under wind. Below, offices, apartments, hotel rooms, and shops pack several parts of a city into the same vertical frame. The arch does not mark an entrance, it creates occupied space high above one. That matters in Suzhou Industrial Park, where a broad modern waterfront needed an immediate center. One structure makes the district recognizable from across the lake. After dark, programmed light traces the outline and turns the opening into a clear urban signal. The building does not merely join the skyline, it organizes it. The common comparison to a giant pair of trousers shows that monumental design cannot control public judgment. A sharper tension in a city known for classical gardens, canals, and low historic roofs. Cannot dismiss its audacity. The Gate of the Orient does not decorate Suzhou's new skyline, it sets the skyline's terms. 600-meter tower narrows at the middle, yet that apparent weakness is where its structure becomes unmistakable. On the south bank of the Pearl River, 2 elliptical grids rotate against each other, wrapping columns and diagonal steel around a central core. The narrow waist is not styling laid over a conventional tower. The outer lattice helps resist wind while remaining more open than a continuous solid facade. Inside, broadcasting equipment, restaurants, observation levels, mechanical floors, and high-speed lifts compete for space. Height here has several jobs: communication, access, revenue, and spectacle. Its openness creates a lifelong maintenance problem. Nearly 600 meters of structure must be inspected, protected from corrosion, reached for facade work, and monitored through typhoons and hard coastal weather. That burden continues long after construction crews leave. A landmark this open survives through repeated maintenance, lightning protection, and constant attention to movement under pressure. Across the river, the tower aligns with Guangzhou's newer civic and business district. It fixes museums, performance, venues, offices, and public space onto one planned urban axis. At night, programmed color makes the grid readable without hiding how it works. The twisting lattice is mesmerizing because Guangzhou turns wind resistance into a clear riverfront signal. Two angular buildings carry one opera house, while its hardest machinery stays out of sight. Opened beside the Pearl River in 2010, its two faceted volumes split the theater between a principal auditorium and a smaller, flexible performance space. Granite, glass, and exposed structural lines meet in sharp folds rather than one smooth facade. Those folds continue into plazas, stairs, ramps, and foyers. This geometry does real work. It draws public circulation between and through the two buildings, turning the ground around a cultural institution into usable civic space. But the hardest architecture is hidden behind the stone and glass. Acoustic isolation, rehearsal rooms, orchestra facilities, loading routes, fly towers, and backstage corridors must operate without disturbing the performance. Audience movement adds another load. Large crowds must enter, separate, gather, and leave while performers, equipment, and stage crews follow different paths behind the walls. The Opera House also carries an urban task. Within Zhejiang Newtown's cultural axis, it faces Canton Tower and helps bind civic buildings to the riverfront. The way I see it, that is the audacity. These angular stone and glass blocks make culture part of Guangzhou's working center, not an ornament pushed to its edge. A tower nearly 600 meters high rises from a city that was still a far smaller border settlement in 1980. Completed in the late 2010s, Ping and Finance Center compresses Shenzhen's extraordinary economic rise into one narrow site in Fuxian. Sit's taper is not cosmetic. By narrowing toward the top, the tower presents less surface to the wind, while a reinforced core, perimeter megacolumns, and outriggers hold the frame steady. The coast adds another pressure. Humid, salt-influenced air works constantly on exposed surfaces, so stainless steel facade elements were chosen partly for long-term durability. Height also turns daily movement into an engineering problem. High-speed elevators divide the ascent into vertical zones, feeding offices, conference rooms, retail links, and observation space without exhausting the central site. Thousands of workers must enter, rise, transfer, and leave through a footprint that cannot spread outward. Refuge floors, mechanical levels, tuned structural behavior, and constant facade inspection make that routine possible. What stands out is not height alone, but the discipline hidden inside it. The slim profile depends on heavy structure, controlled movement, and maintenance that never really stops. That narrow tower earns my admiration because it makes Shenzhen's speed and construction power physically measurable. One roof in Chengdu covers enough floor area to function as an indoor district rather than a conventional building. New Century Global Center stretches roughly 500 meters long, 400 meters wide, and 100 meters high, enclosing nearly 2 million square meters. Scale here runs sideways. Shopping areas, offices, hotels, restaurants, an ice rink, and a vast indoor water park are gathered beneath the same wave-shaped roof. The artificial beach reveals the central idea: outdoor leisure rebuilt under controlled conditions. Glazed sections admit daylight, while screens and lighting manufacture a stable horizon inside. That enclosure buys convenience, but it creates relentless work. Ventilation must move air across enormous volumes. Humidity control, water treatment, cleaning, security, and deliveries must continue at district scale. Distance does not disappear indoors. People still cross long internal routes between work, accommodation, retail, and entertainment, and the building must organize those flows without using city streets. Supertall concentrates a city vertically. This complex concentrates it horizontally. Both demand structure and control, but Chengdu's answer is enclosure on a scale normally reserved for neighborhoods. The true scale is operational. Nearly 2 million square meters must behave as one building every hour of the day. At roughly 2,200 meters above sea level, an ordinary station becomes the gateway to one of rail's harshest operating environments. Xining Railway Station links Qinghai with Lanzhou, Xinjiang, Lhasa, and the wider national high-speed network, while plateau services climb into far thinner air. The concourse is where distance is broken into order. Security checks, departure boards, waiting halls, platforms, and timed boarding turn several kinds of movement into one disciplined sequence. Local commuters share that sequence with tourists beginning plateau journeys, long-distance passengers changing trains, and workers carrying supplies through the regional capital. Every departure depends on coordination measured in minutes. Beyond Xining, the railway meets altitude, permafrost, severe weather, and immense distance. Passenger coaches use sealed systems and supplemental oxygen because thin air changes the basic conditions of travel. That makes the station more than a transfer point. It is the threshold between ordinary intercity rail and a route where landscape dictates the machinery. CIT's crowds also carry Qinghai's wider role. Xining connects eastern China, Tibetan plateau communities, and routes towards Central Asia through a commercial hub built for constant exchange. That rhythm earns my admiration. Distant regions become reachable when engineering, staff, and passengers maintain exact coordination. A road across the Pearl River estuary must disappear beneath the sea before it can reach the other side. The full Hong Kong-Zhuhai-Macau link runs roughly 55 kilometers, combining sea bridges, artificial islands, an immersed tunnel, and connecting roads. The decisive obstacle was not distance alone. A major shipping channel and the flight approaches near Hong Kong International Airport occupied the same strip of water. Engineers answered by lowering about 7 kilometers of the route into an immersed tunnel. Artificial islands join tunnel and bridge, allowing large vessels to pass above while tall structures stay clear of aircraft. That solution then created a harsher engineering test. Salt corrosion, waves, typhoons, passing vessels, and settlement beneath reclaimed ground. Every transition had to remain stable under forces arriving from water, wind, and soil. Movement across the link is not physically simple either. Hong Kong and Macau drive on the left and keep separate border controls, while mainland China drives on the right. Checkpoints, permits, and connecting roads must therefore choreograph each crossing. Concrete and steel solve the water. Administration solves the boundaries. What stands out is the nerve of it, a coordinated route built to cross open water without blocking ships or aircraft. The road crosses this canyon without descending into it, suspended more than half a kilometer above the river. The Baipanjiang Bridge carries the G56 expressway between Guizhou and Yunnan, with a deck roughly 560 meters high and a main span more than 700 meters long. Its towers do not create that extreme height, the canyon does. Before the crossing, a journey had to fall through steep terrain, grind around repeated bends, then climb the opposite side. The bridge cuts across that vertical detour at road level. Construction pushed every task onto hostile slopes. Crews had to anchor towers and approaches into rock, bring equipment through limited access, and assemble deck sections high above the valley. Wind and fog could close the working window. Cable tension, deck movement, drainage, rock stability, and weather still demand constant watching. That vigilance serves more than traffic. It holds together communities and freight routes that the gorge had forced far apart, turning a punishing regional journey into a much shorter drive. The unease and respect come from one fact. A span of more than 700 meters now does what the mountain would not permit. The largest ships serving Shanghai depend on a port built beyond the city's shallow edge. Yangshan occupies offshore islands because sediment in the Yangtze estuary limits deep water access. A bridge roughly 30 kilometers long ties the terminals back to mainland roads and logistics zones. Geography placed the islands in Zhejiang. Engineering made them a crucial working part of the port of Shanghai. Each container enters a tightly timed chain. Ship-to-shore cranes lift it. Transporters carry it to a storage block. Yard cranes stack it by destination, and trucks or feeder vessels take it onward. Automated sections use sensors, control software, remote crane operators, and battery-powered guided vehicles. Their purpose is blunt: cut unnecessary handling and keep each movement aligned. But this is not a machine without people. Pilots, planners, maintenance crews, customs staff, and dock workers keep cargo moving when schedules tighten or equipment needs attention. Soft shore exposure adds pressure, fog, high winds, salt corrosion, and dependence on the Donghai Bridge. A disruption can spread inland through roads, warehouses, and delivery plans. Yangshan's scale is meaningful only as coordination. Boxes, labor, software, ships, and roads must behave as one supply machine. Now, terrain is not merely crossed or occupied. It is recruited at national scale. At Baihetan, a river that cut through the canyon drives a power plant behind a concrete arch nearly 300 meters high. The gorge is not merely an obstacle. Its rock shoulders become structural supports, while the river's drop drives the turbines. Deep inside the mountains, 2 underground powerhouses hold 16 generating units, each rated at about 1 gigawatt. Together, they deliver roughly 16 gigawatts of installed capacity. Water plunges through intake tunnels, turns the machines, then returns to the Jinsha River. Spillways carry excess flows, and help control the river. The electricity does not stay in the canyon. Transmission lines send it over vast distances toward eastern demand centers, binding remote rock and water to factories and cities. But scale carries pressure beyond concrete. Engineers must watch unstable slopes, difficult geology and sediment, while reservoir creation has altered habitats and required communities to relocate. Baihetan makes the bargain impossible to ignore. Low-carbon power and flood management require permanently reshaping a major river. 16 giant machines fill one confined gorge, and the consequences reach across China. The wind resource is enormous, but the hardest task begins after the blades turn. Gansu's turbines stand across vast Gobi and desert wind bases, far from the eastern cities that need most of their electricity. This is not one continuous wind farm. It is a collection of giant power bases, including major clusters around Jiuquan, linked by roads, substations, and transmission corridors. Open land offers strong wind, sparse settlement, and room for machines at scale, but output still rises and falls with the air. Gansu's local demand is much smaller than its potential supply. High voltage lines must carry the power east, while forecasting, storage, and other generators keep the grid balanced. Earlier phases exposed the weak link. Turbines were curtailed when the grid could not absorb or move all available electricity. The human workload stretches across the same distances. Maintenance crews travel between remote towers and work against dust abrasion, icing, and severe temperature swings. Rows of blades prove how much capacity can be built. Substations and cables decide how much can be used. In Gansu, renewable ambition is measured not only in turbines, but in whether the network can make each rotation count. The final power line begins where solid ground ends. Off Jiangsu, Rudong's turbines spread across shallow Yellow Sea waters and tidal zones, drawing on winds steadier than many inland sites. That advantage comes with a harder construction site. Foundations must be driven or anchored into the seabed, then towers, nacelles, and blades lifted from specialized vessels. Electricity moves through cables few people ever see. Inter-Arif lines feed offshore substations, and export cables carry the combined power beneath the water to shore. At sea, the calendar belongs to weather. Tide, wave height, visibility, and seasonal storms decide when crews can install equipment or reach a failing machine. Salt water corrodes metal without pause. Typhoons load the blades, towers, foundations, and cable joints, forcing remote monitoring, corrosion protection, and rapid marine access. The engineering footprint also crosses working water. Projects must negotiate fishing grounds, bird routes, marine habitat, and the coastal sites where buried cables make landfall. Service crews carry the burden behind the clean skyline using specialized vessels, safety gear, and remote monitoring. From Chongqing's layered streets to the Yellow Sea, difficult ground has defined China's infrastructure drive, and each solution creates a new system that must be maintained, negotiated, and paid for. The way I see it, Chongqing's real achievement is not visual shock. It is the refusal to treat terrain as a limit. Mountains force the city upward. Rivers demand longer spans. Dense districts push rail, roads, homes, and public space into the same narrow volume. That pressure has produced an urban form few places could copy without equal skill, money, and endurance. But engineering at this scale carries a warning. Every added layer needs inspection, power, drainage, stable slopes, and constant repair. Complexity never becomes weightless. Across China, the same will shape towers, ports, dams, and renewable energy fields. This is more than spectacle. It shows how national power is built, by turning geography into infrastructure, then accepting the duty of keeping it working for generations. Continue this engineering journey as the series tests one hard question. When geography pushes back, which structures merely impress, and which ones permanently expand what a city can do?